New data modeling patterns have solved one of the most vexing problems of data warehousing and business intelligence: how to get application development started quickly and not suffer from any oversights you might have made during requirements gathering or the design of the target data schema. In the previous screencast, Ceregenics Chief Systems Architect Ralph Hughes introduced you to the first of two hypermodeling techniques, hypernormalization. With this screencast, Ralph will show how a hypernormalized schema can be simplified into a hypergeneralized data model, which will then allow for far greater automated data warehouse development. Hypergeneralization will empower your programming teams to design and deliver new business insights in a fraction of the time that traditional Inman or Kimball data modeling patterns require. But before we dive into the details, let's have our presenter introduce himself.
I'm Ralph Hughes. I help companies leapfrog their competition by using data and information to rapidly define new products, cut costs, and achieve better customer outcomes. I work with Ceregenics, a U.S. consulting firm specializing in data warehousing, business intelligence, and big data analytics. Perhaps you've attended one of my classes at the TDWI or DAMA conferences, or read one of my books that explain how to achieve speed through fast requirements, fast programming, and automated testing. I've taken the best practices from software engineering, agile development methods, and advanced productivity tools and combined them into a method called Agile Data Warehousing. This method allows you to build new information systems with 2/3 less labor using tools that accelerate your work by another factor of 3. To thrive in the global marketplace today, your company must be able to rapidly assemble and expand its infrastructure for big data and business intelligence faster than the competition. You're going to need the acceleration that Agile Data Warehousing can give you.
Many people think that all you need for Agile development is to find a Scrum Master and have them start conducting sprints of team-based programming. However, business intelligence and big data applications are just too complex for plain vanilla Scrum or Kanban. We had to invent instead a highly disciplined software engineering method called Agile Data Warehousing. Over the past 2 decades, Ceregenics created and evolved a wide range of techniques, so that now we have a collection of best practices covering the full range of software engineering disciplines. Disciplines such as requirements, project phasing, database design, quality assurance, and program management. In this screencast, we will continue our focus upon the best practices in the area of database design. It used to be that data warehousing teams had to decide at the start of a project whether they were going to use a third normal form data model or a set of conformed dimensions. Today we have 2 other data modeling approaches to choose from, approaches that are agile and will free us from having to do a big design up front. More importantly, these new data modeling paradigms let us adapt an existing data warehouse when new requirements come along, without extensive data conversion programming. By nearly eliminating conversion programming, agile data designs greatly increase a company's ability to evolve and compete. The 2 agile data modeling techniques are very different, and teams need to choose between them carefully. Hypernormalized forms focus only upon the integration layer of a data warehouse, making that layer easy to start small and evolve as needed. Hypergeneralized data models go even further, making it possible to computer generate the entire data warehouse, not just the integration layer, but the presentation and semantic layers as well. Consequently, of the 2 agile data modeling techniques, hypergeneralization is the more complete and labor-saving approach. This screencast introduces hypergeneralization. We'll start with a hypernormalized model and combine tables with similar functions until we need only 6 logical tables to hold all the dimensional information needed by your data warehouse. The previous video detailed how to take a traditional third normal form data model and hypernormalize it. During this process, the key business entities found in our company's operations became business key tables, shown here in green. The relationship between those entities all became many-to-many linking tables, shown in yellow, even if only one-to-many joins were required. All the remaining fields that served to qualify business entities or relationships were moved to blue attribute tables. Such a model represents a persistent staging layer that provides light integration. This is a crucial foundation for an enterprise data warehouse. The advantages of this modeling approach are several-fold. First, the model can be easily updated to support new entities by simply adding new business key tables, rather than re-engineering an existing table. Second, new relationships between entities also require us to only add new linking tables. Third, new sources can be supported by adding a new set of attribute tables rather than changing the structure of any existing database objects. Finally, and perhaps most importantly, all the tables in a hypernormalized model can be populated from their source by using only a few parameter-driven ETL modules. A green one for business keys, a yellow one for links, and a blue one for attributes. In other words, build 3 reusable loading programs and a driver script to call them with the right parameters, and boom, the ETL for your data warehouse is done. The trade-off for all these advantages is the fact that hypernormalization can more than double the number of tables required to build the integration layer of a data warehouse. This higher number of tables unfortunately complicates our work when we must build SQL to retrieve data for our data marts or for our BI tools. On this point, the competing Agile paradigm, hypergeneralization, starts to look more attractive. As we will see, hypergeneralization allows us to store integration data in a far simpler data model and ultimately allows us to automate the creation and maintenance of data warehouses and data marts. Hypergeneralization builds upon the notion of special purpose tables, so let me introduce this data modeling paradigm by converting a hypernormalized data model into a hypergeneralized one. Here's our starting point, a small subset of a hypernormalized model that shows customers linked to sales orders. The green entities depict separate business key tables for customers and another for sales orders. The many-to-many link in the middle creates a relationship between customers and orders. See the previous video to understand why all hypernormalized links utilize this construct even if they represent only one-to-many relationships. The blue attribute tables show where the hypernormalized model keeps the non-key qualifiers for our 2 business entities. The text below the business key and linking entities reveal the business key values that those entities are tracking. Below the blue attribute tables, you'll see the qualifying values those entities store. Now consider the 2 business key entities. They are structured nearly identically. They contain a column for the business key that identifies unique instances of the entity they represent, plus a surrogate key and some metadata depicting their capture date and source system. The only thing that distinguishes them from each other is the name of the table itself. Well, if those 2 tables are structured the same, then why not store both customers and order business keys in the same table, and just record some metadata to tell us which entity type is represented by each business key record. The same consolidation could be done with linking tables too. So, as our first step towards generalizing our starting model, we make that exact change. Here we have renamed the 2 green business key tables to be simply thing, and we have provided a metadata table called thing type to tell us which type of entity each thing record represents. We have also generalized all the linking records so that they can be stored in a single link table, and we have provided a link type metadata table to distinguish between different instances of linking entities. This change makes perfect sense for links too, since linking tables in our starting model were all structured identically. They held only a couple of surrogate keys that connected them to business key records, plus some columns to contain surrogate keys, capture date, and source system. Now that all business keys and links can be stored in shared tables, we can fold this model onto itself as suggested by this arrow. Here we've lined up all the things and links plus their metadata entities and are ready to combine them. We're going to combine all the attribute tables into a single entity as well, but we'll have to employ one more trick before we do so. The attribute tables in our starting model were all structured differently, so we can't just combine them even with the help of metadata records. We'll have to restructure them so that they all have the same, more abstract design. To do this, we'll convert each column in an attribute table into a name value pair, as shown by the black text at the bottom of this slide. Each attribute record will hold the name of the logical attribute it is tracking, its value, and a link back to the thing record that it describes. A fat, wide table of attribute columns will become a tall, skinny table of attribute records. With this restructuring in place, we can easily combine all the attribute entities into a shared attribute table, as shown here. We have generalized and combined all the tables of our starting model into just 5 logical tables. Note the additional capabilities that this approach gives us that the hypernormalized format could not. The 2 tables across the top of this diagram describe the types of things and types of links that our data warehouse tracks. In other words, they hold the data warehouse model itself, rather than the data warehouse data. The data of our warehouse resides in the 3 remaining tables. Not only have we arrived at a logical model for an enterprise data warehouse that requires very few tables, but that model records the knowledge of our data model in a format that we can populate and query using SQL. This is the key to full data warehouse automation that only the hyper-generalized approach can offer. We're not done yet. We're going to add even more capabilities with an additional concept, temporality. Here we've added an effectivity table between the model and the data portions of our enterprise data warehouse repository. This pink table records the span of time that each set of thing types applies to the data in the warehouse. By adding effectivity, we can make such statements such as products will roll up to product group records until December 31st, but from January 1st onward they will roll up to product type, which will in turn roll up to product group. Note that changing the records in the pink table in no way changes the values stored in the data portion of our enterprise data warehouse. In fact, this pink table lets us impose different models at different times against existing data records, without having to disturb those data records in any way. This allows us to project a given set of data through the lens of multiple models, allowing us to evolve the data warehouse without having to run conversion scripts to update existing data records. This is the key capability that allows hyper-generalized data warehouses to quickly and gracefully support new business requirements as time goes by and the fundamentals of your business change. Our fifth and final step is to place effectivity dates in the structures of all the remaining tables of our data warehouse. With this action, we have temporalized every aspect of the enterprise data warehouse. If a customer is interested in only current data, that's fine. You do not have to use the information stored in these effectivity date fields. But if your customer suddenly decides, I need to know the full history of any given product we sell, you will not need to re-engineer your warehouse data structures nor run conversion scripts on the existing records. The fully temporal nature of the hyper-generalized data warehouse will have saved your bacon. Simply start including the effectivity dates in your transformations when you project data from your integration layers out to your presentation layer data marts, and you can switch from type 1 to type 3 dimensions in no time at all. In fact, the data warehouse generators built on top of hyper-generalized data structures such as these will let you generate data marts that show data as of the time of the transaction or as of the time of the analysis. At any time, you can switch between these as needed. That's Agile. We've touched upon a very important point in the previous slide. The hyper-generalized data model makes it possible for a machine to read and write not only the data but the data model of our data warehouse. So could we draw a picture of the data warehouse we desire and then have a computer read that drawing, automatically converting the drawing into thing types and link types that our business intelligence application needs? In fact, we can. Here is a subset of a data warehouse diagram that hyper-generalized tools can directly translate into thing types and link types. We have entities here. They are organized into dimensions there. We can see a complex hierarchy with multiple roll-up paths for the data warehouse's date dimension here. Transaction data is depicted as solid entities with rounded corners, as you can see in this component of the model. Push a button and the integration layer of your data warehouse will be generated for you, ready to receive data when you run ETL. This is data warehouse automation at its finest. Note that this diagram represents the business model of the data warehouse you desire. In previous slides, you saw the logical model that the computer will use to store the thing and links it finds in this diagram. But do you need to know anything about that logical model? No. Do you need to know anything about the physical tables in which the things and links the computer identifies will be stored? No. Hypergeneralization allows the data warehouse designer to work solely at the business level. Logical and physical data modeling has been removed from the process of delivering business intelligence to the end users. When you don't have to slow down to translate your business concepts into logical and physical data models, think how much time your development teams will save. Such time savings is why hyper-generalized data modeling offers the ultimate in agile data warehouse delivery. To make this more real, let's analyze how the data warehouse automation tool would interpret just a small part of a business model for a business intelligence application. Here we have a product entity that references a product type entity as a parent. The computer would read our business diagram and interpret both the product and the product type as types of things and populate two records in the thing type table. It would also see on the diagram the parent-child relationship between these two entities and create the appropriate link type record. When later we add a vendor entity to the business model, and also a purchase contract entity to relate products to the vendors, the data warehouse automation tool will need to simply add entries for vendor and purchase contracts to the thing type table, then one link type record to capture the relationship between product and contracts, and another for the relationship between contracts and vendor. The past two slides showed how the automation tool interprets business diagram entities into objects in the model portion of our 6-table logical model. Let's look now at how data arriving from the source systems would be translated into entries in the data portion of our warehouse model. Say that the warehouse encounters source data that refers to product X, which is categorized as product type A. The automation tool will have an ETL module that creates an entry into the thing table for both product type A and another entry for product X. So that the system can understand what type of instances these new records are, the ETL would mark them with foreign keys associating them with the appropriate product type and product records in the thing type table. Next, the association of product X to product type A would then be expressed as a new link record, complete with foreign keys to the appropriate product type and product link type records, with yet another foreign key associating product type A and product X. When the ETL next encounters product type B and product Y, it will create a similar set of new records. Finally, when product Z appears and it is associated in the source to an existing product type B, only a new product record would be created. The ETL will associate it to the existing record for product type B. When the data warehouse automation tool reads a business model, it creates records for the thing type and link type tables. But how do we get it to load records in the data portion of the EDW repository? That is, data into the tables for things, links, and attributes. Luckily, those loads can be specified at the business level also, as illustrated here. On the left, we have a source extract holding new data for our product catalog. Using the graphical interface of the automation tool, we create an add modify instance. This is a transformation widget. A widget such as this is specific to one of the object types found in the business model. By reflecting upon that business model, this widget can properly handle primary keys, which it transforms into object IDs. It identifies the remaining columns as attributes. All this is handled automatically for the developer once the flows from the source system are declared. The data flows downstream from the add modify widget is simply a composite set of values to the proper target object, and it is in fact drawn on the ETL development screen for the developer. In essence, the developer can specify the transform while working at a business level. With the built-in intelligence that it acquires from the business model, the add modify widget eliminates most of the programming that is still required by standard ETL development tools. This savings in effort becomes even more apparent when we build ETL for dependent objects. Here is the data transform the developer must specify for loading product entities that reference product types. Again, the developer only needs to provide simple mappings from source to ports on the add modify instance widget, and the data warehouse automation tool will infer the rest, based upon the business model of the target system that the developers provided earlier. Note the flow starting with the product type name. By connecting that to a port for the product type parent object, the automation tool understands that this data flow contains the business identifier for the parent object, and automatically performs a lookup of that value so that an object ID foreign key is loaded into the resulting product records. So, hypergeneralization allows the computer to generate both target data structures and ETL given business level input from the members of your development team. Note that up till now, we've been looking at how this occurs only for the dimensional components of the enterprise data warehouse. We should investigate next whether hypergeneralization allows us to employ business-level specifications to achieve computer generation of transforms for transaction data too. You'll be pleased to learn that the work we've already done to establish the dimensional data makes the ETL development for transaction data considerably easier. Here we see the source extract that provides sales order transaction data for loading into the data warehouse. As with dimensional transforms, the developers need to provide business-level mappings between source elements and ports on a load transaction widget. But from there, the data warehouse automation tool draws a single flow to the target object. When this ETL runs, the tool reflects upon the business model to understand that the 4 codes we've highlighted here actually reference dimensional objects. and performs automatic foreign key lookups for the developer. Just as we saw while loading dimensional data, specifications for ETL of transaction data stays at the business level and is even easier to specify than dimensional transforms. Given that the hyper-generalized automation tool allows developers to create the warehouse and its ETL using business-level objects, it only makes sense that the developers can retrieve data from the integration layer referencing business-level objects as well. To retrieve data, we use something very similar to the query definition tool found in user-friendly applications such as Microsoft Access. The data available is controlled by the business model for the data warehouse. So the objects and attributes appearing in the query definition interface will be readily recognizable by the developers and the business staff as well. Moreover, the business model will inform the query tool whether those elements are dimensions or transaction components. With this insight, users can simply specify the attributes and filters they want, and the warehouse automation tool will generate or refresh a star schema data mart of results for them. In fact, while exporting a data mart, the automation tool will also generate the semantic layer universes or BI frameworks so that the end user access is immediately ready to go. Given all the pieces we have seen in this video, we can now hazard a comparison between the two hypermodeling alternatives to traditional data modeling that Agile data warehousing offers us. Hypernormalization was interesting because if we modeled the data warehouse properly, we needed only a few reusable ETL modules to load the entire integration layer. As cool as that achievement is, it pales in comparison to the capabilities of hypergeneralization that we've seen in this video. Hypergeneralized data models make a far wider range of data warehouse automation possible. Working with a business model and business concepts, we can generate not only the structures in the integration layer, but also the integration layer ETL, the star schemas for the presentation layer, plus the end user views and universes. Rather than just making one layer easier to load, hypergeneralization allows us to computer generate 4 major components of our BI applications, saving a tremendous amount of labor and time. It's natural to ask, what's the price we must pay for all this advanced capability? The price of hypergeneralization is inherent in the highly abstracted data tables we use to store the data warehouse's information. Those tables break every business fact down into a large number of small records, which are then stored in things and links, as well as the attributes and metadata tables. Take the simple statements such as, the Cosmo CM21DU63 cable modem has an SKU of CMX2112. Once that's loaded into the hypergeneralized model, we will have 3 records declaring product and product type objects and the roll-up between them. We'll have 5 records declaring the instances of cable modem and the part number. We'll have another 2 records for the text values of Cosmo and CM21DU63. Among these records, there are going to be multiple foreign key values required as well. Whereas the relational model required 2 records with 1 foreign key, the hypergeneralized model requires 10 records and 9 foreign keys. The hypergeneralized expression of this one simple statement involves an order of magnitude greater complexity in the data that gets stored. With a higher number of intricately coordinated records, loading and retrieving records from a hypergeneralized data repository becomes so complex that enterprise data warehousing teams cannot hope to manually build the load modules and retrieval queries that this system requires by themselves. So the downside to the hypergeneralized approach is that your EDW team will need to invest in a tool that has all this logic programmed and already validated. Luckily, those tools do exist and they are cost-effective as well, especially when you consider the tremendous labor and calendar time they can save a project. We are now in a position to begin discussing the pros and cons of hypernormalized data modeling versus the hypergeneralized approach. Perhaps the first question is naturally, which approach makes the best use of my company's IT dollars? Programming the reusable modules needed for hypernormalized integration layers? Or acquiring and implementing a hypergeneralized data warehouse automation tool that can generate nearly all of the data warehouse from a business model? Further points of comparison will dig deeper into the impact that these 2 approaches will have upon both the IT activities needed to deliver a business intelligence system and also the overall life cycle of that application. To assess these impacts, we would want to ask questions such as these. What do the physical models for each of these approaches look like? How do you calculate and store derived values? What about performance and platform considerations? Can you merge a hyper-modeled application with an existing traditionally modeled enterprise data warehouse? Do the advantages of either hypermodeling approach outweigh the cost of adding more techniques that clutter up my department's DWBI toolkit? Which approach allows the highest value with the fastest possible speed? Look for videos from Ceregenics in the future where we will address these questions one by one. Ceregenics has specialized in Agile data warehousing, and we're big advocates of both hypernormalization and hypergeneralization. We understand the use cases that will determine which paradigm and which implementation style within a paradigm is right for you. We provide experts to work alongside your team as you undertake your next big data, business intelligence, or enterprise data warehousing project. We will collaborate with you on project definition, solution planning, architecture, data modeling, scrum mastering, automated testing, quality assurance planning, productivity tools, and program management.
In this screencast, Ceregenics Chief Systems Architect, Ralph Hughes, introduced the notion of hypergeneralization and contrasted it with another hypermodeling approach that we described in an earlier video. We saw that hypergeneralization allows business intelligence teams to drive the specification and development of nearly every aspect of a data warehouse using a business model and business-level concepts, saving considerable time and labor. As a price for this tremendous power, the number of records stored and queried in the integration layer increases by an order of magnitude, complexity which will require organizations to invest in a data warehouse automation tool. As a compensating benefit, however, development teams will no longer have to invest time and money on drafting logical and physical data models. They will also be able to generate most of their data warehouse directly from the business model for each project. You can learn more about Agile methods for data warehousing, business intelligence, and big data analytics at Ceregenics' website. You can also search the internet to locate our other videos on Agile data warehousing. Contact us if you need a fast start on a new project or a turnaround to save an ongoing endeavor that's not progressing well. Send us feedback on this video, and good luck with your projects.